Hello class, welcome back. We're still on chapter 3, but this is the second half of chapter 3, vector analysis. So in this recording, I will go through the remaining theory material in chapter 3 from our textbook, and the next recording we'll look at problems and examples, and that should finish chapter 3. Okay. All right, so in my last recording, the last thing we did was here on this slide where there's a couple of examples of vector integration. So I introduced you to these ideas and then we stopped. So let me continue. I'm going to expand this and we move on to another section which is also mostly from our textbook, even though I've put it under like a different section 3A-3 in my notes, but most of the material here is also in our textbook in section 3.2 under coordinate systems. So I borrowed most of the slides here from our textbook, and then later on in this section I have some new material not in the textbook, and then we'll come back to the textbook. So hopefully that doesn't confuse you too much. The more important thing is to be able to understand the ideas and the concepts being shown here. All right. So after our brief introduction to vector calculus, where you learned vector differentiation and vector integration, now we do a little more of a deep dive into calculus really. So to introduce us to the idea of calculus in the vector method, we start by exploring what's called differential calculus, which in this case means understanding differential lengths, areas and volumes. Now you may recognize from your early calculus lessons that oftentimes a derivative is written as the limit of something tends to 0, delta x by delta y, where or delta x by delta t if it's a derivative in time, where the delta x is supposed to represent a small quantity, right? A small change in a quantity. So similarly here we are introduced to the idea of differential lengths, areas and volumes. So if you look at this three-dimensional figure in Cartesian coordinates, you see that there is along the x-axis there is a dx. Now this looks pretty big, but in theory you're supposed to imagine this to be very, very small, right? So there's dx in this direction, displacement y in this direction and displacement z in this direction, right? And so dx, dy, dz. And then you can also see that the area, this area for example, is the product of dx and dy, right? Similarly, this area is the product of dx times dz, right? This area. And this area is dy times dz. Similarly, you can imagine a volume which is the product of all three dimensions as dv equals dx, dy, dz or dz. Now, each of these is what we are going to look at not only in Cartesian coordinates but also in cylindrical and spherical coordinates. Okay? All right. So let's get started in this section a little more deeply. So differential calculus involves the use of differential lengths, areas and volumes. Knowing differential lengths, areas and volumes, then by using integration, the complete length, area and or volume of a field can be found. So if we have like a huge field, a vector field here in 3 dimensions, by defining at various locations these small quantities, finding these areas and volumes, and then applying suitable limits, we can measure the complete shape of any kind of vector field. So that's the goal. Okay, that's why we start with differential and then we start applying integration. So in Cartesian coordinates, differential length vector dl, so let's imagine there is a line from, let's say, here to there, right? So that is dl, right? This dl represents the sum of three vector coordinates dx, dy, dz. But if dl is assumed to be dx plus dy plus dz with the proper unit vectors in each direction, then you can write the differential vector as, x hat dx plus y hat dy plus z hat dz. Okay, all right. So having been introduced to that idea, now that was differential length, right? The next thing is differential area vector, and here you have the area ds, right, in three different planes, right? So the xy plane, which is this bottom plane, the xz plane, and then the zy plane, there are three of them. So there are three ds or area formulas, and they are shown as dsx, dsy, dsz with the unit vector x for this plane yz, the unit vector y for the xz plane, and the unit vector z for the xy plane. So there's all three, and so you must take a close look at this figure and understand what these dimensions mean. Of course, you know what the product of these two mean. The area is just the product of the lengths. But more important, each of these vector areas, surface areas, has a direction associated with it. So make sure you understand that also. Okay. So the magnitude ds is equal to the product of the two differential lengths, say dy and dz, and the direction is that of the unit vector of the third length, say x. So if you're talking about the product of dy and dz, the direction is along the x-axis, and so on. Okay. So because this is a vector, each of these is a vector. Next, we define differential volume as a scalar, and that just is the product of all three lengths, dv equals dx, dy, dz, and it doesn't have any direction. Okay. So remember this theory in Cartesian coordinates and take a minute to study each of these formulas in red and black and this volume and understand what the length, the surface areas, and the volume vectors mean. Okay. All right. Now the same concepts in cylindrical coordinates. Now you know that in cylindrical coordinates, the three coordinates we use are r for radius, which is this, right, r. Then phi is an angle, which is the angle starting from the x-axis towards the y-axis on the xy plane, and then z or z in the third dimension as the length from here to here, right? So those are the three coordinates in the cylindrical system, and so here also we define the lengths. The length is defined like this: r dr plus phi r d phi plus z dz. Okay, see there's an extra r here, but otherwise that's because this length is r d phi. Okay, it's not just d phi, it's r d phi, and you can figure it out why this is r dr by trying to assess the length of this from trigonometry. But anyway, that is dl. Similarly, the three areas are dsr, ds phi, dsz, and here's the formulas for each of them. So they are slightly different from what we saw in the previous case, right? Here it's just x dy dz, y dx dz, z dx dy. Here these factors start to creep in. So there is an r in this formula, and there is a r in this formula, and this in the middle, ds phi, doesn't have any additional quantities other than dr dz. Also understand how the direction is for each of these three. Okay, so when we are talking about this plane, for example, this area, which is the product of r d phi and dz. Basically, we are talking about r d phi and dz is this length. This is r d phi and this is dz. So that's the area of this. Then the direction is out in the other axis, which is similar, right, to what we previously learned. And for that direction, you put this little r hat to show that it's in this direction. Okay, so that's why we have these three direction indicators, the unit vectors, in each of these cases. Again, differential volume is a scalar, and that's just the product of dr, d phi, dz with the additional r shown here. Okay, so again, become comfortable with this figure also, so that you understand how the same concept of differential length, area and volume is being translated into the three coordinate systems that we are familiar with. So we have looked at the Cartesian or rectangular, we have looked at the cylindrical. Next, as you can imagine, is the spherical, right? So the spherical is a little more complicated in the sense that now it's not easy XYZ axis, right? Now we are looking at things in the R, capital R, the phi and psi, right? This is psi. Oh, sorry, this is R, theta and phi, not psi. R, capital R system, theta and phi. So here again we have the length definition first, and the R does come into the picture in both of these. So you can see, well, that is for the length, right? Next we talk of the differential area vectors ds. S in this case is about area, and again the area is the product of two things in each case. So for example, the area here, and I've tried to show you this also with a picture from another book, but this area is, in that other book they use the small r, which is a little confusing. I should have changed that. But anyway, DSR, right, in this direction. Now remember, R is measured like this, right, towards the outside of the soccer ball, as I've already shown you. So R continuing in this direction, it has a direction like this going out, and this area is the product of this, right, r square sine theta d theta d phi, right. So this portion on top, so we are calculating the area of this, right. This is almost like a small rectangle, but not quite. That's why you have this complicating factors. The length here is r sine theta d phi, and then this side or this side is r d theta. So once we have these two sides, we then just multiply them and pretend it's like a real rectangle, even though we know it's not exactly. But nevertheless, the product of these two, right? Actually, I should put a little r there. I'll do that later. So think of this as a capital R. So r sine theta d phi times r d phi or d theta gives you this r square sine theta d theta d phi, and that's how you get DSR. Okay, so hope you understood how this or this is derived. Similarly, we have for the other two directions, there is one in this direction, right, pointing down, and then there's one in this direction pointing out, right. So those two are what you see here, and they have these formulas. So DSR, ds theta and ds phi have these three formulas, and each one of these vectors, unit vectors, is in the direction, the third direction, same logic. Lastly, the differential volume dV is a scalar. It doesn't have direction, and the magnitude of this dV is r square sine theta dr d phi or dr d theta d phi. Okay, so this is the volume. So how is each one of these formulas derived? If you need more explanation or you're not quite believing all this, I suggest you take a look at our textbook. In some cases, not all cases, the derivation is shown, or you may need to look at more advanced textbooks in mathematics to really understand how they are derived. But for our purposes, you need to know that in each of the three coordinate orthogonal systems, you have formulas for differential length, one formula, three formulas for differential area, and again one formula for differential volume. And you need to know how to calculate these, or at least look these up, because there is a table, as you can imagine, somewhere. Let's see if I can quickly find it. Yeah, here, sorry, I think it may be in the other direction. Yeah, I think I showed you this right in the beginning. Yeah, here is the table. This is just conversion. Okay, well, there is a table somewhere. We'll find it eventually, but for purposes of being able to solve problems and all that, you don't really have to remember each one, but you need to know where to look for them. Okay, all right. So that finishes our introduction to this whole differential length, area, and volume. I suggest you also become comfortable with this, with these figures, so that you understand how the length is defined in each case, how the three areas are defined, and how the volume is defined. Okay, all right. So with this, I will move ahead. We hit some examples which I will wait to come back to after we finish the theory. So let me skip slide 56, 57, 58 is also an example, 59 is a problem, 60 is a problem. All of this is related to the differential business, so let's hold off on that. And now we come to another important topic called line, surface, and volume integrals. Now this wasn't as clearly shown in this textbook, in our textbook, so I had to go around and dig up information from a few other sources. So hopefully this will help you. But I think this is a key piece to understand, why we derived the differential, stuff, and why we defined it, and then where are we going in the future, right? What new stuff are we going to do? And this section 3-A kind of links the two together. So again, I'm going to define three things: line, surface, and volume, similar to the length, surface, and volume we saw in the previous section. So let's look at what a line integral is. So the line integral is the integral of the tangential component of field A along a curve or path L. So here's a path, right? Just think of A to B as a path, and it is in a field A, right? A field A is a vector field. That means that every location, every spot on the field, it has direction and magnitude. And so the line integral is the integral of the tangential component of field A. So if this is so you need two things here to understand. First is the field, and then a path or a curve. So in this case, AB is a path. It can be a curve, it can be a straight line, all are allowed. But along this path, in this field, you first find a tangential component. A normal component is a perpendicular component. So a normal component would be coming out of the page, right, or looking at or coming in your direction of your face. But this tangential component, as you see here, dl, is along the page, right, along my computer screen. So if you take the integral of the tangential component of field A along curve or path L, that is the definition of line integral. So look at the mathematical definition. You write an integral, put an L there, and then the scalar product, the dot product, right, A dot dl, which is a scalar. So, and this gives you the component, which also you know, I think, along a certain direction. So that can also be calculated as this. So that's the definition, okay. Now if the path of integration is a closed curve, right, so we talked about AB. Now if you go through A, B, C and then back to A, it's a closed curve. If the path of integration is a closed curve such as ABCA in the figure, then it becomes a closed contour integral, which also has another name called the circulation of A around L, okay, circulation of A around L, and that is written like this. So A with a circle, L dot dl, meaning this path L is closed, okay. Now note that dl here, and later we'll use these kind of formulas with ds and dv. They're all as defined in the previous section, right, where we did differentials, okay. So that's an introduction to something important called line integral on slide 61. And I have a problem here that will clarify. Sorry, I hit the wrong button. I have a problem here, but we'll come back to this in a bit. So let's keep moving. And here I introduce you to the idea of, slide 63. Yeah, the idea of the area integral or the surface integral. Okay. So the surface integral also is called the flux, and now you see that psi, which is the Greek letter psi shown like that. So the surface integral of vector field A through S at any point, and S is a surface, right? Previously I talked about a line. Here S is a surface. It can be in 3 dimensions, while a line is only in 1 or 2 dimensions, right? So the surface integral through S at any point is called the flux, and the flux has this formula: psi equals A cos theta, which is this A, times ds, or it can be written like this. Okay, the surface integral, and this is a vector. It has the ds is always a vector, if you remember from our previous section on differentials. So you're basically, actually this may not be a vector, I'm sorry, flux can be a scalar. So let's hold off on defining that until we do a problem, then we'll understand it. But psi is always, well, let me say this, definitely the integration happens on 2 variables, right? Because area is always the product of 2 variables, x and y, right, or phi and psi, theta and phi, or r and theta, etc. So the 2 products, the 2 variables need to be integrated, and hence the double integral, right? So I hope you guys are not scared of double integrals. I'm sure you have done it in the past, but to calculate the flux or the surface integral, we're going to have to do a double integral. Lastly, if the surface is closed, similar to what we saw previously where we talked about a closed surface, or calling it closed line integral, called it circulation. Here, if the surface is closed, then we put that little circle, and you'll see some examples of here's a good example of a closed surface, right? This is a closed cylinder, while this is an open surface. So if the surface is closed, then we write it with the circle in the center, and this is the formula. Okay. All right. I'm going to move ahead. And here I have a problem on surface integral, but we'll wait to do that. But let me move on to the third type of integral, which is a simple integral called the volume integral. Okay. And the volume integral, as you can imagine, dv has three products, or right, it's the product of three different variables x, y, z. So this is a triple integral with a certain scalar also included in this, and this is called the volume integral. So I introduce you to three different integrals: line integral, surface integral, and volume integral. One of them is a single integration, surface is a double integration, and volume is a triple integration. Now I also have an example actually from the textbook, from our textbook on the volume integral, but we'll wait to do this in the next recording. Then there's a problem on volume integral, so let's also wait to do that. Now we come to a very important section. Actually, the important section from our textbook is on the next slide, slide 69, 3-4, and 3-4 is a long section. It introduces you to many new things, but before we get to 3-4, let me still, I'm on my extra section 3-A.5, and here I introduce you to something called the del operator, which is a simple concept but used a lot in the remaining chapter, remaining part of this chapter and the remaining part of your course actually. Maybe you have already been introduced to the del operator. If you have done a course in mathematics on vector analysis, I'm sure you have seen this. I don't know what the practice is at CQUPT, whether you would have covered all this in a math course. Maybe you have, in which case this should not be new. So what is a del operator? If A is a vector function of more than one scalar variable, say x, y, and z, or A is written as A, x, y, z, remember this is a vector function, okay? Then you can define the del operator like this, and it's three definitions really: Cartesian, cylindrical, and spherical. The easiest is in the Cartesian or rectangular coordinate system, where del just means you take a partial derivative of this function on the x direction, the y direction, you take a partial derivative in the y, and the z direction you take a partial derivative in the z. So this is just an operator, right? It means nothing until you have an A to put this to. But the operator by itself has a name, and it's called the del. And so and immediately you jump into these partial derivatives. In this case it's on x, y, z. In this case it's on r, phi, and z in cylindrical, and in spherical capital R, theta, and phi. Okay, and the definitions are slightly more involved. Here it's simple. You can see it's just dou by dou x, dou by dou y, dou by dou z. Here it's dou by dou r, but here dou by dou phi, there's an r in the bottom, and then dou by dou z. Here it's dou by dou r, and then again there is an r, dou by dou theta, and then this is a little more complicated. You have r sine theta in the bottom, in the denominator, and then dou by dou phi. Okay. So three definitions. Again, if you will allow you to generally have a table of this when you're taking an exam, so don't worry too much. But you must know where to quickly find all these. Okay. All right. So using the del operator, there are four important applications, which are four sections in the next tab, in the next part of our chapter. Okay. So looking at section 3.3-4 in our textbook, we will cover each of these. So, we understood the del operator as a mathematical operator. Using that, we first define the gradient of a scalar written as del v. Then we talk about the divergence of a vector A written as divergence div A. Then we have the curl of a vector A written as a cross product. This is a dot product, this is a cross product of this del operator, right, which is a vector crossed by A. And then lastly, we have something called a Laplacian of a scalar V written as del square V. So, these four things are what we are going to look at in the next 15 minutes to cover the theory of this chapter. Okay, all right. So, this last section in my notes was something I created to introduce you and revise vector calculus. So, we looked at vector differentiation, vector integration, then we jumped into differentials, differential length, differential area, differential volume. We followed mostly what was in our textbook. Then we came up with definitions for line integrals, surface integrals, volume integrals. Then I introduced you to the del operator. Okay. So, with all that background, let's start looking at what's in this section 3-4 in our textbook. Again, I told you we are going to look at the gradient, the divergence, the curl and the Laplacian, four different things in this section. Okay. So, starting with the gradient, actually they are each in a different section by itself in the textbook. So, there is 3-4 on page 69, then there is 3-5, 6 and 7, okay, to cover each one of these: gradient, divergence, curl and Laplacian. So, what is 3-4? It talks about the gradient. What is a gradient? The gradient of a scalar field V is a vector that represents both the magnitude and the direction of the maximum rate of increase of V. That's one definition. Okay. So, we don't use the vector version of the field, we just take the scalar version, and you'll see how that is done. But for now, just remember that the gradient operates, the del operator is applied to the scalar portion of a field. So, here I have defined it in V, but here we jump into T. It's a little confusing, maybe I should just stick with T here, but anyway, let's look at the definition. If T is a scalar function of x, y, z, then del T, or known as grad T, also gradient, grad, is x dou T by dou x plus y dou T by dou y plus z dou T by dou z, or z. Okay. So, that is the definition of grad T. Next, we have something called the directional derivative of T along the unit vector AL. So, we saw this definition of grad. There is another thing that we talk about, which is the directional of derivative T. To get that, all you need to do is to take the grad T that you calculated here, do a dot product with a unit vector along a certain direction, a certain vector, only need the unit vector along that direction, and then you can say the directional derivative dt by dl along that length is this product. And from this formula you also get, because delta t is nothing but the difference between two things, right? So, if you take t2 minus t1, which is two different points, then you can take this dt here and integrate this, right? So, integral of dt by dl is done in this fashion. Okay. So, integral of grad t dot dl over a certain pair of limits P1 and P2, that gives you the delta t. So this is another formula that is useful for certain kinds of problems. Okay. So just remember these, much of this will become clear if we do problems obviously, but these are basic definitions that you need to be aware of. What is the grad t? What is a directional derivative? Then here's a little drawing that talks about, it just points out P1 and P2, right, in a scalar way. And so this P2 minus P1, if you wanted to calculate, you can use this formula to find the distance P2 minus P1. Okay. Now we have other ways of doing this. We learnt about them, how to find the distance between 2 points. You can always create a vector of this vector P1 P2. You can write a formula for this vector P1 P2 and then do a magnitude calculation. That is one way to find it, or you can use this formula to also find the length of the vector. So this is another way, another useful benefit of defining this grad t. Okay. All right. So with that, I will move on to a next slide, slide 70, where all three definitions of grad t in the Cartesian system, which we just saw, in the cylindrical system with r, phi and z coordinates. See how grad t is defined, gradient t, and in the spherical system where we have capital R, theta and phi, and see how grad t is defined. Okay. So three different definitions of grad t. Actually t is pretty much the same, it's just a scalar. The delta, the del, right, the del operator itself is defined differently for these three coordinate axes, coordinate systems. Hence the three different definitions of the Cartesian, the cylindrical and the spherical. Here's some more material on the gradient. So it satisfies some distributive and associative rules. So you may find this useful in some problem solving. Okay. I'm going to move on because we still have to finish the other three. We only looked at gradient so far. We still have divergence, curl and Laplacian. Okay, so example, we'll wait. Another example on grad, we'll wait, and we come to divergence. So divergence is more like it deals with areas, right? So here we talk about this product. Here's a definition. Okay, so as I told you, if you take the del operator and you do a scalar product on a vector, then you call that divergence E or div E, which is dou by dou x of Ex, dou by dou x of Ey, dou by dou x of Ez, where Ex, Ey, Ez are scalar components, right, of E. So that is the proper definition. But to understand this, you need to understand a lot of these other definitions. Okay, so let's spend a couple of minutes trying to figure out what's going on. So what we see here is what's called he calls it a parallelepiped. So it looks like a cube, right? But I think a parallelepiped is a general version of a cube. Cube always has same sides, but this is can have different lengths for each dimension. But anyway, in a parallelepiped, he is showing a field E with flux lines, right? And this little parallelepiped or cube is sitting inside the field, and the flux lines of a vector field are passing through a differential rectangular parallelepiped of volume delta V is delta x, delta y, delta z, right? So this you understand. So now if you take the surface integral, right, this is a surface integral with an S there. Remember we talked about line integral, surface integral and volume integral. So a surface integral of E dot the area ds, and you know ds, right, it has at least two faces, right, or two dimensions in each direction. So if you do that product, then what you come up with is the flux going out from that face, from that side of the parallelepiped, and that is div E multiplied by this delta in volume. So here's a good definition, this is from our textbook. By shrinking the volume delta V to 0, we define the divergence of E at a point. Now we are pretending this is a point, right, one point in the field, even though it is a complicated point, but we define, but assuming everything is shrinking here to a small point, so that delta x, delta y, delta z are all going to 0. By shrinking the volume delta V to 0, we define the divergence of E at a point as the net outward flux per unit volume over a closed incremental surface. So this is the mathematical definition. I don't think you need to worry too much about this. If you know how to do a divergence and you know how to use these formulas, you're okay for, for this course. But if you're really interested in what is it that I am talking about when I say divergence, here is the definition. So I'm going to leave you to struggle with that a little more, because I do have a few more slides to cover. So field E, for example, can be defined in terms of the divergence also by looking at these drawings. So A, for example, is said to have positive divergence if it contains a source of field lines. So this point P seems to be a source and all the flux is coming out of it. So such a situation, we say it's a positive divergence of this field, whatever is the field, A or B or whatever. Similarly, you have a negative divergence where everything is going in, and then you have a divergence less where nothing is coming from inside, everything is just going through, it's coming from outside and then is leaving. And such a field is called divergence-less, and if you calculate the divergence, it comes out to be 0. Okay? Alright, so these are three definitions. And the divergence-less field is also called solenoidal. Okay? So here's another important theorem related to divergence. So what the theorem says is, the divergence theorem that the total outward flux of a vector field through the closed surface S is the same as the volume integral of the divergence of E. So if you did the divergence and then did the volume integral, which is a integral in 3 dimensions, right, 3 variables, that actually is nothing but a surface integral of a closed surface, and the two are equal. So this is an important theorem. We are going to look at some problems related to the theorem. Okay. Moving ahead. Here is a summary of all the definitions, the gradient, the divergence. We haven't looked at curl and Laplacian yet, but they are also included. And you can see the formulas for each one is in this table. Okay. So here's a problem, here's another problem. Okay, curl. So curl, we go back first to my definition of a line integral, right? I told you what this is, and we talked about a circulation which is around the closed path. So next slide, slide 80, we talk about the real definition of curl. So curl is a vector product. So del is operating on a field. When you do that, you call it curl, and it also has this definition of limit delta s tends to 0, 1 by delta s, a surface a line integral over a closed path b dot dl. Okay, and here's a bunch of definitions all related to this. Okay, please read them. I like this definition at the bottom, so let's quickly look at it once. And here's a picture to show you what the curl is or how we go around the path. Remember, we are talking about a closed path in a field, right? Both that is important to understand. The curl of B is an axial or rotational vector whose magnitude is the maximum circulation of B. Remember, circulation means going around a closed path, right? Maximum circulation of B per unit area as the area tends to 0. So that's the magnitude, and the direction is the normal direction of the area when the area is oriented so as to make the circulation maximum. So if you're going around an area in a maximum direction, then the direction that is normal, that is perpendicular to that area of maximum circulation, that direction is the direction of curl. So again, curl has both magnitude and direction, and this is how you define the magnitude and this is how you define the direction. Okay? Alright. So here's a little more. A curl at P points out of the page. Curl at P here is 0. And a curl, a field that has the calculation curl comes out to be 0 is said to be a conservative or irrotational field, meaning there's no rotation going on around that a point in the field. So here's the definition of, or the formula in the Cartesian system. So if you start with a field definition B, which is in 3 directions x, y and z, and each one of these coordinates is a scalar in 3 coordinates x, y and z, or in 3 variables, then the formula is a matrix determinant, as we have already seen for a cross product, and here is the formula to use when we are calculating the curl. Here are some formulas for associative distributive. Let you take a look at it. Here's some examples. A very important theorem to go with a curl definition is that the curl of a vector can be reduced, which is a dot, which is cross product, can be reduced to a line integral. Okay, so Stokes' theorem converts the surface integral into a line integral. The surface integral of the curl of a vector over an open surface S equals a line integral of the vector along the contour C or the path C bounding the surface S. So this is your Stokes' theorem. So there's a right side and there's a left side, and we'll do some problems to prove that Stokes' theorem works. Okay? Alright. So here's some problems. We can wait for later. Okay, the very last slide, and I apologize, we have gone over by 5 minutes, but this is important to finish in one lecture. So what is the very last thing in this chapter? Something called the Laplacian operator. So if you take the del operator and apply it twice, then we come up with what's called the Laplacian of V. And this del operator operates on a scalar V, not a vector. Okay, so first you do a scalar del V, which is the gradient, and then you do a dot product of the two. You still get a scalar. So this, well, you might get a vector actually. Yeah, I think we may get a vector here. So if you do that, then you yeah, actually I have an example. No, you get a scalar. I'm always confused, but so you end up with a scalar. Laplacian operation gives you a scalar, but you do first a grad and then one more dot product, and if you do that, when you do a dot product, you're doing a divergence. So you do a divergence of the gradient of a scalar, and the result is what you get is called a Laplacian. Okay? Alright, and then we have a couple of problems which we'll do in the next recording. So take a few minutes, go through this material, read the textbook many times, make sure you understand all of the theory, and I will come back with some problems on this material.